This is Unit 5 of 3D Modelling and Animation Module F21MA. And today what we're going to do is we're going to talk about collisions. And this is basically based on the code from Peter's ActionScript 3.0, at least the collision calculation is. So before we look at the details of the collision, we're going to see how to detect the collision. So we can use Flash's simple hit test to see whether when the bounding boxes are over each other. But because we're dealing with billiard balls here, we're dealing with spheres, or rather a circle, a 2D case, and therefore we need a distance-based hit test as well. So we'll look at both of those quickly. Flash's hit test essentially tests whether or not bounding boxes overlap. And there's a very simple syntax, which is shown down here. We can take the hit test object method of one ball and test it with the argument set to the other ball. So here the blue ball's method is being tested with the black ball as the argument, and this would return true, and we would know that these bounding boxes are overlapping. Now, of course, this doesn't tell us whether or not the two spherical objects, are actually touching. So once we've triggered once we know that the bounding boxes are overlapping, then what we can do is we can do a distance test. And this is just straight Pythagoras, where what we're looking to do is to see whether or not the square of the difference between the x's plus the square of the difference between the y's in terms of the centre of the balls is less than some limit, which is the distance between the two balls when they're just touching squared. We don't take the square roots of these because square roots are expensive, so we just leave everything in their squares, and that's a bit cheaper. So first of all, what we do is we use Flash's hit test to discover whether or not we've got overrounding. We've got in the pudding box, and then what we do is we test for the distance. Once we've done that, then we can start implementing the billiard ball physics, and this code comes from Peter's. Let's have a look at the basic equations. We've got momentum, which is P equals mass times the velocity. Momentum equals mass times the velocity. And we know that this momentum is conserved. Okay, so the total momentum before the collision is equal to the total momentum afterwards. And this is the equation that we end up with here on the bottom. We've also got basic energy equations, kinetic energy equation. Again, this is conserved, so we've got half mv squared on the first ball, half mv squared on the second ball, and again, these must add up to be the same before the collision and after the collision. So that we know that both the momentum before the collision and after can't change, and kinetic energy before and after can't change. Now, if we take those two equations, then what we can do is we can work out the velocity after the collision of the first ball and the velocity after the collision of the second ball, and these are the basic equations. These are the equations in one dimension. Okay, so what we're doing is we're looking at these dimensions. We're looking at these equations, in this case, in the vertical dimension. Of course, in terms of the implementation, what we have to do is we have to look at it in terms of angles. So now what we're going to do is have a quick look at how we calculate this when we don't have a convenient vertical bounce or convenient horizontal bounce. And the trick is to actually convert this into one of those two easy cases. So what we do when we've got the point of collision is we calculate the angle between the centres. Now we're going to rotate this to the horizontal. We do the calculations along the x-axis to conserve both momentum and kinetic energy. That gives us our change in terms of the x velocities. And then what we do after we've done this calculation is we rotate it back again. So here we rotate it back again, and we've done our collision calculations. And that's basically it. All right, now what I'm going to do is I'm going to show you some of the code. So if I look at my example here, then I can take one of my fireballs And as usual, I've got string attached to it, which means I can fire it. And you'll notice that when it hits one of the other balls, it starts moving around. And again, I can start these moving around. And here we go. And of course I can reset them to an initial set of conditions, and when they hit each other, then the bounces are reasonably realistic, as long as they're not going too slowly. Okay. So what I'm going to do in the next video is basically explain how I've changed the fireball, this basic fireball, to include this collision behavior. Thanks very much.